They will read this article in here. Basically, understand control use communication it also require extensive power compensation and filter. It's the first diagram basically talk about weaker system, especially on the infrastructure side, we will communication failure. And if the other side we have a weak system, it's going to be a problem. So in this case, most of the people will choose BSC as the inverter and the LCC rectifier. With the technology advance, the growing need for transmission power, BSC become interestingly increasingly popular in the utility system compared to the LCC. BSC offer a lot of benefits. They have no commutation failure, active and direct power control independently, and they can serve as a stack, which means they can supply direct power during the fault to boost up the voltage. In this scenario, we for this it will be a very interesting topic in the future for us to take a look at whether this direct power can be supplied to the inverter side or not. Okay, now next is as the topology MMC. Talk about MMC, a lot of applications in reference 1 to 4, go to reference later, but not limit the HVDC transmission line system. Fact device, wind, renewable, all widely used VSC. Therefore, we had to address the shortcoming of the LCCs and also understand the advantages of MMC. The LCC MMC creates a normal hybrid transmission that connected to it with AC systems. The new configuration have advantage. Okay, so let's talk about the advantage. For instance, for instance, incorporating the MMC on the inverter and not only voice communication tools but also otherwise independent control of the P and Q mode. I'm assuming in this exercise or the example is talk about PQ mode all the time. I'm assuming in this inverter and is PQ control. Yeah, LCC on the other hand, LCC is cheaper than MMC. If we come this one end, okay, the cost wise it will be attractive too. In particular, MMC LC hybrid system capitalize on economic benefit of the LCC, also a technological advantage of the MMC. So the reason we talk about the technology advantage of the MMC is because we avoid the conflict in the LCC. The LCC only more has a conflict. But when it comes to the DC fault, if half bridge MMC still have a problem, okay? The conflict it will avoid conflict. If the voltage is too low, or sometimes we will conflict on the LCD if it's on the inverter. So this manual is to develop a simulation example for LCD MMC hybrid transmission system and provide a standardized control for MMC station. Okay. Figure 1 illustrates the bipolar HVDC system in the example case. Each pole consists of two sets of 12 poles LCC. Okay. as a rectifier. Two MMC in series serve as the inverter. Two sets 12 poles. Okay, is this monopole? Oh, is this bipole? This is bipole, not monopole. So two 12 poles. I think I'm assuming one of them they are positive pole, another one is negative pole. Nice. The LCC site incorporates two groups of LCC and Y delta transformer, eliminating the fifth and seventh harmonics. Okay. On the MMC, the topology can be set up half bridge or full bridge MMC and MMC. Okay, the DC or mixed module. Okay, this is interesting. You can do this option. This can be an option, study option in the future too. I'm not sure can I save this. Save as? Yes, we do. We can save this. Different name next time. I will open this. Okay, so this will offer a static to do. Another thing is a stack and provide a stack. That's another thing. Also interesting to look at whether this act as a stack. The DC side connection equals two HB lines, one at positive end, another one is negative end. Okay, that's bipole. First return is used to point. Big one shows the present from the specification of the LCC MMC side and transmission line system. We have 800 volts here, and the transformer have this 530 transformer. Okay, so this 500 line quite big line here, and one this, and okay, 12 volts. This is a 6 volts. No, this is 12 volts. This is 12 volts. So we have 12 volts. 12 volts. Positive pole and 12 volts. Negative pole. This is the transmission line here. And 2.5, 3.5 on the MMC side. Surprisingly, the MMC side the strength is bigger than the rectifier. That's how you can operate bigger. You can do bigger, right? Okay, so parameter setting. Parameter setting for LCD. We contain all the variables and PI controller in here. So the standard frequency is 50 Hz. That's different. Maybe highlight this too. Base parameters. Base parameters for one single pole is 530. Okay, for the transformer, we do see 530 here, and so we have this 530 step down to a certain value, and this value 170.3 times what? 4. Okay, that's 800. Close to 800. Okay, that's fine. So this rated value, the power that given on Singapore is this one. So that's 3,200. That's too much. That's a lot of power to neural. Um, I think that's for balls, right? Because what I see here is this 1,600. I think that's for a single ball. If that's for a single ball, this link is 400. Yeah, this link is 400. So why we have 800? I'm not sure. This is 400 and this link is this for each MMC. Okay, for each 12 poles. Okay, I see. For each 12 poles because we have two 12 poles here. That's why I make it 3,200 something. Yeah, I see. In total, I see. Times two. Okay. We are talking about this one. Okay. And for this is just one. Okay. So that's a lot of power. So that's for single pole, right? Negative power for one single pole, right? So in total is notice the AC connect to the LCC in valuable with connection. AC is connected to a source. This variable source is just by a controller, which controls the AC voltage after the source impedance to be weighted value. For example, in this example, the LCC AC voltage is set at this 2.5 and 80 degree. The series and the inductance are set for this. Respectively, the parallel is this. Okay. So why is adjusted by a controller AC source, which controls the AC voltage after AC source voltage. So this source voltage is set by a controller. Okay, that's interesting. Let me open the case for now. See what does she mean by the source is controlled by uh, source is controlled by controller. I don't know what that means. Okay, so we have here on the rectifier side the system parameters. Open here, there's a source. Okay, AC source 80 voltage. What does it have? There's a PI controller. So that this voltage is controlled by something. And it goes you have an auto or manual that has some auto. Okay, so when we do this, what this AC voltage and voltage control do? We have so basically there's a signal sense in called TU1 volt. However, there's the error message here, error on the line voltage. There's a PI controller here. Then split out the error message times this voltage equals to where this one from? This okay, much okay, that's the magnitude. Okay, that's magnitude this controller is control the magnitude of this by doing this PI controller. So what is does this fault mean? So this is something I want to look at later. It seems like it measures the RMS voltage. Then once it measures the voltage in the line base voltage, then times 3, that will be line voltage, then goes to a bypass filter. A bypass filter goes to 2U1 VL. This is measure. This measure phase voltage. This measure voltage at where we measure this. Copy, Control F, then search. Where we measure this. Once we search, we have a bunch of. This is this one. PCC fault control signal. So that's this. There's a one fault control. We search this. Yeah, we search this PCC. Isn't that what we searched? Okay. This is a lot of times. Okay. Yeah, that's what we search. We just want to know where this one is measured. Where's this node? Okay, this one. Lastly, measure in here. That inside the controller. This one. Where's this? Where is this one? Let's see. This is LCC. So that's measured. Okay. So one is upper, one is lower. I'm assuming, yeah. So that's the terminal, the point of deliver. POD point. I do see that. What's this label? It's called PTU1, PCCA, TU1 bus, terminal U, terminal 1 bus. Is that give us point of PCC point A? Okay, that makes sense. That makes sense. Where we use point of deliver point, and we get this P and Q. Okay, okay. When we do the 10 millisecond measurement, that makes sense. Yeah, that makes sense. There's a meter, so we measure the AC side, and we get line voltage on here, and we get the per unit value in here. Once we get per unit value in here, and we have this one AC reference one. So 1 minus something give us an error message, and this error message gonna go here. What is this? Is this add? Yeah, add. This message, so this add this, and times this goes to here, then this one goes to here, goes to here. So why you need to control this terminal voltage? AC grid terminal voltage control. Why you need it? Because I know this is the major voltage. Major voltage you have your reference. You obviously want to keep your um, reference is equal to 1 per unit. If it's not equal to 1 per unit, it will generate error message. Error message will go to here, and this one and this one plus together, it won't be 1, right? It won't be 1. It will be something else. It will be 1, either 1 plus 1 or 1 minus 1. Then goes to here, then goes to here, then goes to the voltage. Why we need this? AC grid terminal voltage control. So what is the purpose? It seems like whenever there's a deviation on the AC side, for example, there's an AC fault, so this voltage will drop. Whenever this voltage drops, so it will generate a positive error. The positive error goes here, goes to the control value, positive control value. Positive control value goes to here, to add this thing, and it goes to. So whenever there's a fault, it will maybe increase the terminal. Is that right? Right? Why we want to do that? Okay, is that because it's trying to mimic the machine? Okay, that's something we can discuss later. Now, we just quickly go through the rest of this document. So, AC grid connect to a variable AC voltage source with okay. The variable AC source is just by a control which control the AC voltage after the source as to be a rated value. Okay, to be a rated value. You see, that's why I see 1.0 here probably. Yeah, but why we turn the fault or run the disturbance, we need to adjust the output of the terminal voltage. That's something I'm not sure. The base calculation of the one single pole. Okay, so right now we have a station 1 VLL rated voltage. If we want to get the peak value, we divide by root 3 times root 2, we will get the peak value. This, see figure 3. Yeah, that's base calculation of the LCC. That's it's okay. We get the base. Yeah, this is how we get base. Line to line, this is all the parameter here. All the parameter here. Parameter set for MRC. That's 2.2. So we will finish this 2.3. Then we will go right. And then we will standard frequency and this their rating, AC voltage. Note, whenever there's a note, I want to read this. Whenever there's a note, I want to read because that can be important. The VOS number circuit, that's for LCC, right, is used to specify the numerical oscillation in the real-time modeling. The time constant for this number segment is recommended to be twice of the simulation time step. Here, the snap transfer is 60 milliseconds, which is twice of the signal. Okay, this is not vast number, right? So this can be important to know in the RTDS. For example, snap time content is 60 milliseconds, the time step is 20 seconds. So when we go to this circuit, uh, we go to the key setting, and we want to know, we want to make sure it is 30 milliseconds. Then next, we want to go to the LCCE, and when we open, there must be a snapper circuit setting in here. What is current monitoring? Obviously not. Var parameters? Yes. This is number circuit. So we set in here. Capacitance on, off, those the value in here. So I just wonder where all this value is defined because there's a dollar sign here. It tells us tells us uh, numbers, all the parameters. Let's go back to the menu. Uh, I remember in here. Okay, here we can show rated parameter for PU measurement. I'm assuming all this value will be something in here. So, for example, this number circuit 0.01 of this ohms, this ohm on off, and this is number circuit 300 ohms, and this how from this number circuit resistance value and the capacitance value are we can calculate this by simply using the R times C, that will be a time constant. The 300 times 0.2 times 10 to the power negative 6. It will give us 86. It will give us RC. Yeah, so that give us 60 microsecond. Exactly. I will, if I want to comment this, oh, yeah. So is that just for RTDS I'm wondering, or is that can be, like, can be different way? R times C equal to 0.2 10 to the power negative 6 given 6 microsecond. Okay, this is how we get it, right? So I just wonder if I search this, it should tell me where they define all these constants. Unlike PSCAD, oh, do we have a global setting here? No, unless PSCAD, we can set all the parameter value in the global thing. This is not. We can search only in the draft, match the whole word, regular expression, case sensitive. This, search this. Okay. Okay, it show us this to understand. Yeah, that's in here. That's in the first one. Because that's the one with the dollar sign. The one with the dollar sign. Yeah. We see that some the thing in here. Let me open maximize how to make it smaller. We do see y in here, y is in here, 0.2, right? 0.2, 0.2 microhenry, that's correct. That's the value we define on which hierarchy box. This very nice. It tells me where the hierarchy box. Which hierarchy box? This hierarchy box that use it. Oh, this is nice. Which is I think this new searching feature is definitely winning it. It's good. It's good. I really like. Okay, so right now I know where they define the parameter. It seems like here define all these parameters. So for now, we understand this node parameter MMC, that's 2.2. We have note the strength of the AC grid that's on the inverter is determined by the RC connection with the ideal AC source. Exactly. In this example, the strength is 3.5. So that's one of my questions why we have to keep this high. Total power resistance. Okay, this is good. This is good. We later on we can back calculate whether it makes sense or not, right? Because we have our own Excel sheets to calculate um, the system strengths. We can use that Excel sheets to verify this whether it is correct or not. So in this case, I want to highlight two one more time. Okay, 80 degrees variance value Rx, X, XR ratio. Note the is around this pole. Okay, okay. So it's a small, it's like half size of our transmission line. It's longer, twice like this. Each pole delivers this value. Okay, the current is 4 kA. Right? I understand that. The runs. Okay, so let's talk about the voltage drops. Something like okay on the DC line. Therefore, the rated DC voltage is set at you have to do that. You have to do consider the what I mean is this voltage drops will be a different value if the power delivered is not at this value 22 volts can be a small number or large number depends on power. If it doesn't hurt if we rate it higher, I mean transiently it can be go higher. The reason we put it in here does that mean we can have a smaller and economically cheaper. In this case, blah 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 is calculate this. Okay, the peak value and this, and also the inductance 2 pi frequency this plus this plus this. The equivalent arm inductance for each fundamental frequency is being used to do okay. So that's understandable. And per unit impedance for 2-arm inductor at second harmonic frequency. Okay, that's CSCC, right? So that's a different value. Understand? Now, the parameter of this goes to here, here, here. Okay, that's delta 1 transformer. Okay, that's all. It's very detailed. It's very detailed. Explained here. Module total is 200 watt and half and full. If this mix option, okay, so if there's a mix option, 50% will be half, and of will be full. That's one. So that's okay. So I had to not only uh, record this video, but also I want to take some notes. Okay. RTDS. What's the question regarding the system strings? Why the system strings on the rectifier and the SCR on the side is why in LCC set is 2.5. Now, RC circuit, that's understandable. Then, on the question, that's okay. The rate MMC what something remember constant in the simulation circuit must be 2 times larger than time step. But in PSC it's 4 or 5 times. But now it's okay. I just keep it 2 because observatory wave that one is different Euler. That's understandable. Thing I learned here is AC water control on the source. That's something I don't understand. Another thing I learned from here is okay. So the idea I got from this paper is half of the floor that's and half of them are that's definitely something option we can take a look at. I don't even know how to model the floor. Another thing is backup and that's something awful. So let's go back to the paper. Now we have to go through all the parameters here. So note ST2 G1 SM, that the submodule must be equal to this half and 4. Otherwise, an unnc component will pop up. Okay, that makes sense. So there's an option you can do mix option. So I usually want to go to the things to do to try. I want to do things to try is mix. To look in the case is first one is mix option in the case in the MIC module. Okay, now let's mix. I know first we want to add the comments. Now different file always has ARM adapter. ARM adapter 18 important in the case. Use the each lag. So what we use in the PSCAP case, I open a PSCAP case right now. That's SOP. Open. This